The first hero of this course was a hash set. Lesson 1. The GTA Story. T0ST replaced an array scan with a structure where checking "Have I seen this before?" cost the same tiny amount of work whether 10 items came before or 60,000. I showed you the fix. I never explained the machine. 11 lessons of machinery later, you're ready. And here's why I waited. The only order 1 lookup you've met is array indexing. Base address plus index times element size. 1 multiply, 1 add, 1 load. But that trick demands an integer index. Real programs look up usernames, URLs, session tokens. So the entire question of this lesson fits in one sentence. How does the string Alice become an array index? Answer that, and everything you filed away in Lesson 1, average order 1, worst case order n, the occasional rebuild, follows from arithmetic you already own. Start with an ordinary array. 8 slots, indexed 0 through 7. Now take a function, call it hash, that eats any key, a string, a number, a tuple, and spits out a fixed size integer. Don't worry yet about its insides. Picture a recipe like walk the bytes of the key, mixing each one into a running number. Say hash of Alice comes out to 2347. Too big for 8 slots, so take the remainder. 2347 mod 8 is 3. The value for Alice goes in slot 3. That's an insert. Now the lookup, an hour later. Someone asks for Alice. Run the same function on the same bytes. 2347 again, mod 8, slot 3. There it is. 1 hash, 1 mod, 1 array access. Notice who's doing the real work here. Slot 3 is base address plus 3 times the slot size, the exact order 1 arithmetic from Lesson 3. The hash function adds nothing magical. It just manufactures the index that arrays already knew how to use. A hash table is an array wearing a key-to-index converter. 3 things make that converter trustworthy. Determinism. Hash of Alice must come out identical every time, or the table breaks. Insert under one number, search under another, and the value is simply gone. Uniformity. Outputs should spread across the integers like rain, no favorite slots. Any bias turns one slot into a crowd, and crowds are the slow case arriving early. And speed. This function runs on every operation, so it gets a handful of nanoseconds. A few multiplies and XORs per byte, not a ceremony. Real ones have names. FNV, a few lines long. Murmur, the workhorse inside a lot of infrastructure. And SipHash, which carries a secret key. The reason why is a story coming later in this lesson. 1 disambiguation, because the word hash is overloaded. These are not cryptographic hashes. SHA-256 spends hundreds of cycles making output irreversible. Table hashes spend a few cycles making output spread. Different jobs, same unfortunate name. And one piece of honest fine print. Hashing an integer is near free. Hashing a string walks its bytes. So the lookup is really order key length, plus order 1 for the table. For Alice, 5 bytes. Nothing. Just know which part of the bill the order 1 covers. Now the problem that defines the entire data structure. 2 keys can land in the same slot. Say Bob hashes to 9011. Mod 8, 3. Same slot as Alice. That's a collision, and I want you to feel how fast these show up, because intuition says rarely and arithmetic says constantly. You may know the birthday version. 23 people in a room, and it's a coin flip that 2 share a birthday, with 365 days to spread across. Tables are worse. 3 keys into 8 slots, and there's already a 1 in 3 chance that 2 of them share. Scale it up. 1,000,000 slots. And by about 1,200 keys, a collision is a coin flip. 1,200 into 1,000,000. And no cleverer hash function escapes this, because pigeonhole arithmetic doesn't care. Infinitely many possible keys, finitely many slots. Some keys must share. So collisions are not a failure mode. They're line 1 of the design brief, and there are exactly 2 classic answers. Answer 1. Separate chaining. Every slot holds, not a value, but a pointer to a linked list. Lesson 5 structure. Back on payroll. Insert Alice. Slot 3. New node. A list of 1. Insert Bob. Slot 3 again. No panic. Prepend. Slot 3 now chains 2 nodes. Lookup Bob. Hash, mod, slot 3, then walk the chain comparing actual keys. First node, Alice. No. Second node, Bob. Yes. 2 comparisons. Collisions just add a short walk. And now the worst case you filed away in Lesson 1 is visible to the naked eye. If the hash is terrible, or someone forces every key into one slot, the hash table quietly becomes a linked list. Lookup, order in. The whole game from here is keeping chains short, and the average chain length is just items divided by slots. Hold that ratio. It gets a name in a minute. Answer 2 throws the lists away entirely. Open addressing. Every entry lives in the array itself, and a collision means walk forward. Insert Alice, slot 3, empty, done. Insert Bob, slot 3, occupied. Try slot 4, empty. Bob lives at 4. The walk is called probing, and trying the very next slot is linear probing. Fancier footwork exists, quadratic jumps, a second hash picking the step size, same idea. Look up Bob, hash to 3, find Alice, not Bob, step to 4, found. A probe ends 2 ways, find the key or hit an empty slot, which is proof the key was never inserted, because the insert would have stopped there. And that proof is exactly what makes deletion subtle. Delete Alice, leave a hole at 3, and the lookup for Bob now hits empty at 3 and declares him missing. He's right there in slot 4. So open addressing can't just erase, it plants a tombstone, a marker that says dead, but keep walking. Lookups step over them, inserts may reclaim them, and a table that collects too many rebuilds itself clean. So which answer wins? Chaining is simpler, and it tolerates crowding gracefully. But Lesson 2 already told you the deeper story. Walking a chain means each node is a separately allocated object, somewhere out in the heap. Every step is a pointer chase, a possible 100 nanosecond trip to RAM. Chains commute. Linear probing checks slot 3, 4, 5. Adjacent entries, the same cache line or the next one, which the prefetcher is already hauling. Probes stream. The 2 collision strategies are the 2 memory access patterns from Lesson 2, wearing hash table costumes. And modern engineering voted with the hardware. Python's dict, open addressing. Rust's hash map, a design called Swiss tables, born at Google. Go's built-in map moved to Swiss tables 2 around version 1.24. The Swiss trick, in one breath, keep 1 metadata byte per slot, packed together so a single wide instruction checks 16 slots worth of maybe at once, and the real entries get touched only on a likely hit. The internals are a rabbit hole. The headline is Lesson 2, Paying Off. Hardware likes neighbors. That ratio from the chaining scene, items divided by slots, is called the load factor, and it's the dial every hash table lives by. 8 slots, 6 entries, load factor 0.75. It reads as, how full is the table? And it trades memory for speed. Keep it low, waste slots, stay fast. Let it climb, save memory, pay in probes. Chaining feels the dial gently. Load factor 1 means chains average 1 node. Comfortable. Open addressing is a different animal because probes need empty slots to stop. And as empties get scarce, something ugly compounds. Picture slots 3 through 9, all full, one long run. A new key that hashes anywhere in that run, 3, 5, 8, walks to the end and parks at 10. So the run grows. So it catches even more keys. So it grows faster. Clusters feed themselves. Back of the envelope, Half full, a miss probes 2 or 3 slots. 90% full, around 50. So real tables never let it get there. Python resizes around 2/3 full. Java's hash map, 3/4. Different numbers, identical policy. Cross a threshold, rebuild. And the rebuild is the moment I promised at the end of last lesson. Every hash table you've ever used, occasionally stopping to remake itself. Here's why it can't cheat. Allocate a bigger array, 16 slots instead of 8. And every home address changes. Because the home was hash, mod capacity. Alice, 2347, mod 8, slot 3. Mod 16, slot 11. The keys didn't move. The street got renumbered. So a resize must allocate the new array and rehash every single key into its new slot. Order in. No way around it. Sounds expensive, but you already own the defense. Lesson 3's doubling argument, verbatim. Double the capacity each time, and the rebuilds land exponentially far apart, so the total work of every rebuild ever stays proportional to n. Amortized, order 1 per insert. Same bank balance arithmetic as the dynamic array, plus a hash per element moved. But remember what amortized does not promise. It never said no single insert is slow. One unlucky insert pays for the whole rebuild, all at once. For most programs, that pause is invisible. For some, it's a production incident. Picture a table holding 50 million entries in a hot service. Some innocent insert crosses the threshold and now rehashes 50 million keys before it returns. Every request queued behind it, waiting. On the latency graph, it's a spike with no visible cause because the code that triggered it did nothing unusual. It was just the unlucky one. Redis, the in-memory database that is one giant hash table at heart, refuses to take that pause. Its answer is incresil rehashing. When a resize begins, Redis keeps both arrays, old and new. Reads check both, writes go to the new one. And every operation that touches the dictionary migrates a small batch of old entries on its way through, with a background task nibbling at the rest, until the old table drains and gets freed. No single operation ever pays for the whole move. The cost is bookkeeping and a window where two tables coexist. The prize is no spike. Same amortized total, spread fine instead of lumped. Now the worst case stops being theoretical. December 2011, the Chaos Communication Congress in Berlin. Two researchers, Klink and Velde, pointed how web frameworks parse a request. Every form field goes into a hash table. The field names are chosen by the client, and the language's string hashes were public, deterministic, unkeyed. So an attacker at home can pre-compute thousands of strings that all hash to the same slot. Send them as one post request. The server's table becomes one long chain. Every insert walks it. Inserting n keys costs order n squared, and a single request, a few hundred kilobytes, pins a CPU core for minutes. PHP, Java, Python, Ruby, all vulnerable the same week. Remember Lesson 1's exact phrasing. Make the worst case so rare you can price at the average. This attack is why rare isn't enough. Against an adversary, the worst case has to be unguessable. The fix is SipHash, a fast hash that mixes in a secret key, chosen randomly when the process starts. Same table, same slots. But nobody outside can predict where any key lands, so nobody can manufacture collisions. Python, Ruby, Rust, that's the keyed hash from earlier in the lesson, and this talk is the reason it exists.
The randomness has a visible side effect, and Go turned it into a design statement. Hash order was never meaningful. It's whatever the hash scattered. But programmers kept shipping code that accidentally depended on iteration order. Code that broke whenever a seed or an implementation changed. So Go randomizes map iteration on purpose. Differently, every single run, so the dependency can't even form. Need order? Sort the keys.
That's the API lesson. Never depend on hash order. And there's one contract left on the keys themselves. A key must hold still. Lesson 4 told you strings cache their hash and dictionary keys must not mutate. Here's the full reason. Insert a key, its hash says slot 3. Now mutate the object. Its bytes changed. Its hash changed. Every future lookup probes slot 6. Nobody moved the entry. It's still sitting in slot 3, unreachable, lost, without ever being deleted. That's why Python refuses a list as a dict key and accepts a tuple. Second clause, equal keys must hash equal. Java spells it equals and hash code. Override both or neither. Break either clause and the table doesn't crash. It quietly loses things. Which is worse? So cache the promise out. A hash table is an array plus an index factory. Average order 1, because a decent hash spreads the keys, and a load factor cap keeps the crowd small. Worst case order in, real enough that attackers weaponized it, and now made not just rare, but unguessable. The occasional rebuild, amortized away by doubling, or spread thin when the latency budget demands it. That's the structure you reached for, fully explained. But look at what the hash function destroyed to buy that speed. It scattered the keys on purpose. Ask the table for Alice. Instant. Ask for every user between Alice and Bob, alphabetically. It has no idea. The smallest key? No idea. Everything near a key? Gone. Scattered by design. Order 1 lookups at the price of all order. The next structures pay the opposite way. They keep every key sorted. They answer ranges and nearest and smallest, and they still run in logarithmic time by borrowing the one move you trust completely by now, halving. Binary trees and the 4 ways to walk them. That's next.